First of all, thank you very much to Log Conference to allow us to present this tutorial on graph rewiring. I mean, it's very exciting, and we are planning to go from the theory and the basics to even to applications in fairness to explain like the full landscape of this field, and I hope you like it. So thank you very much for coming. We are going to be presenting the graph rewiring from theory to applications in fairness tutorial. It's me, Francisco Escolano, Nuria Oliver, and Edwin Hancock. First of all, you have the resources here. We have a web page in which we have the link to the code, and we will publish the slides and the video after the tutorial. So another goal of this tutorial is that you can have these resources for a long time there, just not only today. So feel free to save these links for your toolbox. The main outline is here. I'm not gonna go very deep, so only the main goals that we have with this tutorial is explain the motivations and challenges of rewiring, then do a little introduction to spectral theory to be everyone in the same page, and then move to transductive rewiring. That is a line of methods that done rewiring in a special way. Then we are gonna move to inductive rewiring, that it's like a more novel way to perform rewiring. We will end up like explaining the fairness applications of this rewiring. After that, we will have a panel discussion with Petar Velikovic, Marinka Sidnik, Francesco De Giovanni, and Francesco Fabri. So I hope you like it, and I leave the stage to Francisco Escolano to explain the motivation of the graph rewiring.
Well, so for motivating graph rewiring, we had to describe, generally speaking, graph rewiring as the pursuit of the optimal graph structure for a downstream task. So it depends on the task. So for instance, in graph classification, we had the graph on the left and where we are interested in to classify. And it depends what type of graph we have. So the idea in graph classification of rewiring is just skeletonize the graph so that the most informative subgraph is visible. So for instance, in the graph on the left, we have two approaches for rewiring the graph. One of them is bottleneck preserving. So we decide to preserve the bottleneck and to remove things, edges that are not important for information flow between these two communities. Doing that, we can discriminate between graphs whose differences are in the bottleneck. But if what we want is to discriminate between graphs based on the properties of the graph in the communities, what we can do is to minimize the gap and preserve the structural, so the topology of the communities. Where are the differences? This is what happens. For instance, these are examples of the collab data set, where we have that is better discriminated by bottleneck preserving than by gap preserving. And in other cases like the SVM, for instance, SVM models is the contrary. So this is what we can do doing rewiring for graph classification. But in general, all this kind of work is aligned with the need of being more powerful than the 1WL test. And there are many works in the area, like distance codings, positional encodings that make GNNs more expressive. And well, the idea is to discriminate between graphs based on some attributes in the nodes which reflect the structural role of these nodes in the graph. So the idea is to motivate in this tutorial is to motivate integration between this approach to graph classification and isomorphism and the rewiring approach. What rewiring can contribute to the isomorphism-based approach. If the task, for instance, is node classification, so we have that in this very heterophilic graph, it is interesting that some nodes, which are, for instance, here, can reach the hub, so that they can find some nodes with the same properties. So the rewiring should preserve this kind of paths, and this is one of the reasons where in heterophilic graphs it is important to do a rewiring that preserves the access between distant heterophilic nodes. So the idea, and in homophilic networks is very easy to do the rewiring, because all we have to do is to reduce the gap. In heterophilic networks, we have to be more careful. Well, this is the figure of Cornell data set where I explained before. Well, so the problem motivating the rewiring, one of the problems is that GNNs use original design according to the smallness principle, that is, structure and node labels are correlated. This homophily, and we can measure homophily in terms of edges, or in terms of nodes, or in terms of class. But the important thing is to reflect the correlation between the structural labels. For instance, we can use the digital energies. This is a classical work, has been done in semi-supervised learning, to minimize digital energies is just using the smoothness principle, or we can use associativity, just use the Pearson correlation coefficient between the degrees of the nodes. So the heterophilic case, as I said before, is the most complex, because we have different radius of propagation. So we have three problems. This is well known. We have the underreaching. We can stop the propagation before reaching one of the distant nodes of the same class. Or we have over smoothing if we increase the radius of diffusion or propagation. So we cannot understand, or we can remove the properties of this node, or we are over squashing, where in a case where the information is blocked by, for instance, by a bottleneck. For instance, this here is an example of rewiring as a solution. In this kind of in this graph, so if we make propagation, the bottleneck is not allowing to communicate this part of this community with this part of share the same label, and basically what we're going to have is that misclassify of these nodes and classify all these nodes here. But if we enlarge this bottleneck, so this is possible to preserve these two communities better. So broadly speaking, the key challenges or the desiderata for graph rewiring is that our graph rewiring should be principled, should be expressive, interpretable, have to explain what the rewiring is doing, align with the task. So we are doing node classification or graph classification or link prediction, as parameter free as possible. So we'll distinguish between integer rewiring and is subject to some parameters, and well, there's another important thing is that it's global propagation. Try to remove the bottleneck if we have some kind of squashing. Reduce the computational complexity. This is especially addressed to the computation of some spectral measures that take quadratic or cubic complexity. So in terms of avoid no dedicated processing like CUDA, things like that. And very important, one idea of graph rewiring is to rewire the graph in a proper way. In the classical edit graph problem is that preserve the graph, which is edit, that it has to preserve the properties of the original graph as much as possible. If not, it's because the task demands that this is not satisfied. Well, I'm going to introduce Edwin Hancock for explaining some basis of spectral theory.
Just picking up from where Francesco left off, and my job is really to provide some of the introduction to the spectral theory of graphs. So this is how it fits into the overall plan of the tutorial. So let me begin by just introducing some of the basics. We're going to be dealing with undirected graphs, and the graph is going to consist of a node set and an edge set. The nodes are represented by the set V, have labels 1 to n, and the edges are represented by the set E, which are a subset of the product of the node set. So it's usual to represent a graph using an adjacency matrix. We're going to move on to from this representation to the Laplacian later on in the talk. But the adjacency matrix is a representation of edge connectivity. It has elements 0 along the leading diagonal, and an element is 1 if there's an edge connecting a pair of nodes. That is to say, the pair of nodes I and j belongs to the edge set, and is 0 otherwise. And we can also deal with weights. So rather than having zeros and ones in the matrix, we can have real valued weights on the connecting edges. So what I want to do is to talk about what happens if we define functions on the nodes in the graph. So what I'm going to define is a function f, which takes me from the node set of the graph onto the set of reals. And for instance, and used throughout this talk, we're going to consider the case where the function f from the node set is on to a binary set which has elements -1 and +1. And in this talk, I'm going to color the negative elements in blue and the positive elements in red. And so here you see an example of a function, two different functions defined on the graph, and the blues and reds indicate whether the node function f takes on a value -1 or +1. Okay, so we want to define a little bit more about these functions and choose some ones which can be useful leading on to the graph rewiring problem. So if we have a function where the values are all the same on the different nodes, this is the harmonic case. But more interesting for the problem of dealing with graphs, and particularly partitioning the graphs into sets of disjoint nodes, is the example I've shown you here. And here we have a piecewise harmonic function where we have two different disjoint sets, A and B, where the sets of connected nodes are indicated by the same binary indicator. And what I want to do is to set this problem up so that we can define it in terms of a cut problem. What I'm going to do is define a cut associated with bipartitioning the graph into two disjoint sets of nodes. And the cut is defined on the left-hand side of the screen. So the cut defined in terms of these two disjoint sets A and B, which divide the nodes of the graph as I said, into two disjoint sets, is just given by the sum over nodes in I and in A and nodes in J, the sum of the edge weights on those connecting edges. And so when I've defined the cut in this way, what I can attempt to do is to find a function f that minimizes the average cut between the sets A and B. And I've defined the average cut at the bottom of the slide. The average cut for the bipartition into the sets A and B is the cut for A and B divided by the number of nodes in A, plus the same thing divided by the number of nodes in B. And generally speaking, finding this a function that will optimize this cut is an NP-hard problem. So one way of addressing this problem is to use Fiedler's theorem. So Fiedler's theorem shows how you can measure the variability of the optimal solution to the minimum cut problem that I have shown on the previous slide. So here we take a vector whose elements are -1s and 1s. And what we want to do is to try to define the variability associated with the elements of this vector defined by the minimum cut on the graph. And what Fiedler's theorem says is that the variability associated with the second eigenvalue of the Laplacian matrix minimizes the ratio between the variability imposed by the structure of the graph and the unconstrained case. So I can write this down in terms of the following ratio. I sum over all pairs of nodes. I multiply the edge connectivity or the weight by the difference between the values of the function or the components of this vector x at connected locations, and square that, and then just divide by the same thing where I, instead of imposing the edge structure of the graph on the variability, I simply take the total variability over all elements of the function. So this is an example to show the effect of the different eigenvalues of the Laplacian matrix. So if I take the first eigenvalue of the Laplacian matrix, then the elements identified by the eigenfunction are all associated with a value 1. The 0 eigenvalue of the Laplacian is associated with your 1's vector. If, on the other hand, I take the second eigenvalue, that is to say the second smallest eigenvalue, and I shade the nodes according to how positive or how negative they are, then I get the following visualization of the graph. So we see the blue negative nodes here and the red positive nodes here. And the darker the shade of red or darker the shade of blue, that means how positive or how negative the elements of the second eigenvector associated with the second eigenvalue are. Okay, so let's probe into this in a little bit more detail. To do that, I'll need to define the combinatorial Laplacian. The combinatorial Laplacian is the degree matrix minus the adjacency matrix, where the degree matrix has the degrees of the nodes along the leading diagonal, and the degrees are just the number of connecting edges for each node, or the sum of the weight associated with the connecting edges. So here I've written down the Laplacian matrix. We have the degree of the nodes along the leading diagonal, and then we have the negatives of the weights associated with those with the edges of the graph on the off diagonal. And if you look at any row or any column of this matrix, then the sum of the elements is equal to 0. So the Laplacian matrix is positive semi-definite, and that means that if we take the trace of the transpose of a function times the Laplacian matrix times the function, then that quantity is always greater than or equal to 0, provided that f, the function, is in the set of reals. So the trace of the Laplacian is exactly gives us exactly the variability that I was talking about in the previous slides. So if we take the trace of the Laplacian pre-multiplied by the transpose of f, post-multiplied by f, then that's just equal to -1/2 the sum over all pairs of nodes, the weights associated with the edges, times the difference in the function values at the nodes connected by an edge. And so the trace of this quantity simply computes the variability of the values of the function over the pairs of nodes connected by edges in the graph. and we refer to this quantity as Dirichlet energy. And so an interesting property of this of the Laplacian is that if we take the eigenfunctions times the Laplacian, then those satisfy the following condition, and each individual function value is just given by the 1 over the degree times the values of the function multiplied by the weight summed over all connecting weights at a node. So let's talk a little bit about the spectrum and the eigenfunctions of Laplacian. So the important quantity in dealing with this discussion is something called the Rayleigh quotient. So if I have a vector x taken from the r to the n, then x transpose times x times L times x divided by x transpose times x, so these are scalar quantities, is going to be a number in the set of reals. And we can think of the product x transpose times x as being a measure of unconstrained variability over the nodes of the graph. So if we look at the individual eigenfunctions of the Laplacian, the first eigenvalue, which is 0, is associated with the harmonic solution of the eigensystem. Then the second eigenfunction is defined by this eigenvalue equation, L times F2 equals lambda 2 times F2, and the eigenfunction is the Fiedler vector. And the Fiedler vector is associated with minimizing this quantity here, which I defined previously. It's just the constrained variability divided by the unconstrained variability, and with the condition that the solution vector is not a unit vector or a multiple of it. Okay, so each of the eigenfunctions is each pair of eigenfunctions is perpendicular, orthonormal, and the eigenvalues satisfy the following condition, where the 0 eigenvalue, the first eigenvalue is 0, its multiplicity tells us the number of connected components in a graph, and the second eigenvalue is the Laplacian, is the Fiedler associated with the Fiedler vector, and it minimizes this quantity here. So let's just now look at the eigenfunctions in order of increasing eigenvalue and visualize them again, showing increasingly positive and increasingly negative components of the eigenfunction in increasing shades of blue and red. So here we see the first solution where all components of the eigenfunction are equal to 1. Then we have the solution associated with the Fiedler vector, and you'll notice that this has the tendency to separate the graph into two populations of nodes associated with different clusters according to how positive or how negative the elements of the eigenvector are. And then we have different patterns emerging as we look at the eigenfunctions associated with increasing eigenvalues. So the Fiedler vector is associated with a solution that minimizes the cut between the two sets of nodes. So next topics I'd like to address are introducing the heat kernel on a graph, and then talking about the commute time on a graph. So let's talk about how we start by decomposing the Laplacian matrix into an eigenvector matrix phi, a diagonal eigenvalue matrix lambda, and the transpose of the eigenvector matrix. So here is the eigenvector matrix. I have the eigenvectors or eigenfunctions as columns, and then I have a diagonal matrix with the eigenvalues along the leading diagonal. And so I can write the Laplacian as a sum over eigenmodes, the eigenvalue times the outer product of the eigenvector with itself. So the heat kernel, which I'm going to call H, is defined as the, in terms of this partial differential equation. The heat kernel, the partial derivative of the heat kernel is just equal to minus the Laplacian times the heat kernel. And you can rearrange this differential equation by taking H over onto the left-hand side and dt over onto the right-hand side, integrate both sides, and that will give you an exponential as a solution. And so here is the heat kernel written as an exponential function of the Laplacian with time. It's e to the minus t times L, where this is matrix exponentiation. And I can write that expression for the heat kernel trace simply in terms of the matrix of eigenvectors of the Laplacian, the exponentiation of the eigen value matrix with negative time times the transpose of the eigenvector matrix. And this is the expression written out in full with the eigenvector matrix and its transpose, either pre and post multiplying a matrix which has the eigenvalues exponentiated along the leading diagonal. So we can, if we like, we can rewrite this the heat kernel K of T as a series expansion, basically a matrix Maclaurin expansion in terms of different powers of the Laplacian matrix times different powers of T. So it's basically identity matrix minus T times L plus T squared divided by 2 factorial times L squared and so on and so forth. This allows us to look at the behavior of the heat kernel at small and large values of T. So when time is close to 0, the heat kernel is just equal to the identity matrix minus the Laplacian matrix times time. And as T goes to infinity, now the second eigenvalue and the Fiedler vector begin to dominate the heat kernel, and it's given approximately by e to the minus lambda 2 times T times the outer product of the Fiedler vector with itself. Whoops. So why is the heat kernel important? Well, we can use it to define heat diffusion, or the behavior of a continuous time random walker on the graph. So we start with the following situation. At t equals 0, each node has a unit of heat associated with it. And as t goes to infinity, heat diffuses across the graph, driven by the Laplacian according to the heat equation. And the heat equation just says that the heat at time t plus 1 is given by the heat at time t multiplied by the heat kernel. And this leads us to trying to characterize a graph using something we referred to as the heat kernel signature. And so the heat kernel signature of a node is the trace of the heat kernel evaluated at that node at each of a series of time steps. And so we write this as H sub T, the heat at node T, at time t at node I and j. And this is just the probability that a lazy, continuous time lazy random walker starting at node I hits node j at time t. And here what I've done is I've illustrated the heat diffusion across the graph with time going from t equals 0 to t equals infinity. Another property of graphs, which is going to be useful when we come to the rewiring discussion, is something called commute time. So commute time between a pair of nodes is defined to be the hitting time of a random walker leaving node to leave node I and arrive at node J, and then the hitting time for it to return again. So why is commute time an interesting quantity? Well, if you consider the problem of, for instance, taking a graph representing a road network, and that road network is the road network along which you have to travel on your commute from home to work every day and then return again. If the one of the connections in the network representing one of the roads you normally take in your path from home to work is deleted, normally that will not actually prevent you getting from work. What you'll do is you will take an alternative path. And what the commute time does is it actually averages over all possible paths between a pair of nodes, the time taken to travel and travel home again. And so if a particular link is missing or deleted for some reason, the commute time is only marginally affected by that. And so basically commute time measures the distance between a pair of nodes in the graph in a manner which can be robust to deletion of individual edges. So we can also define something called the resistance distance between a pair of nodes, and that's defined as the commute time divided by the volume of the graph. So it turns out that the commute time between nodes U and V is given in terms of the eigenfunctions of the eigenvalues and eigenvectors of the Laplacian matrix. And this is the expression for it. It's just the volume of the graph. We sum over all non-zero eigenvalues. So we don't visit the smallest eigenvalue of the graph and take the difference between the eigenfunction at node I at node U divided by the same thing for node V and square it. So what you'll notice is that this is a measure of variability of the components of the eigenfunction I, summed over all eigenfunctions, but ignoring the zero eigenvalue, the all ones eigenvector. And it also has the form of a Euclidean distance between the eigenvectors weighted by the inverse of the Laplacian matrix. So effectively the pseudo inverse of the Laplacian matrix. Okay, so that leads us to the idea that we can use the eigenfunctions of a Laplacian matrix to embed the nodes of a graph into a space where the Euclidean distance between a pair of nodes is just the same as the commute time between a pair of nodes. And given that this looks like the Euclidean distance between eigenfunctions weighted by the inverse of the eigenvalues, then this is the embedding that will actually give us an embedding of the nodes of the graph into a vector space where the distance between pairs of nodes is just the same as the commute time between a pair of nodes. And so the embedding is given by the square root of the volume of the graph times the inverse, pseudo inverse of the eigenvalue matrix of the Laplacian. So that's the inverse discarding the zero eigenvalues times the transpose of the eigenvector matrix. And here I show an embedding of a graph. I assume it's the same graph that I've been using in the other illustrations. And you see that the different nodes associated with the different clusters of nodes that we would like to bipartition are separated into nice clusters by this embedding. Okay, so I think that's more or less the end of my section of the talk. So I'll now hand back to Antonio, and Francesco to continue talking about the rewiring problem.
Oh, thank you very much, Edwin. So before starting the next section, I reminded the attendants that there's examples of codes of every section of the tutorial. In particular, there's code about the Laplacian. Everything we put in the slides are in the code. And you have 4 collab notebooks: Introduction to Spectral Theory, which is this one, Transductive, Rewiring, the lowest bound, and the city layer. So for questions of time, we're going only to operate a little bit in live with the city layer, but you can simultaneously with this with the exposition of the concepts of later on, you can come back to the code and run the examples and see understand better understand what is happening with these kind of examples. Right. I want to talk about transductive. When we refer to transductive rewiring when there's an input graph and we apply a representation of the graph, which is going to be used once. So it's not going to be used for predicting new incoming graphs. And later on, we will talk about inductive rewiring, which is how to learn the rewiring, and then when a new graph is coming, you can apply what you have learned to compute the rewiring. So there are 2 main examples of this kind of transductive rewiring. One of them is related to the idea of the heat kernel. There's the kind of diffusive rewiring. So diffusion processes like the heat kernel provide principal methods to link distant nodes, because what we want to do is to link separated nodes, and especially if these separated nodes have something in common. So the idea is that spatial message passing need deep layers to leverage high order or distant neighborhoods. So in these graphs, we have structural noise. There are some edges in the real graphs. Very often, they are noisy. This means that they are not correlated with the distribution of nodal features or including the labels. So this is interesting to use some spectral principles. We can run spectral GNNs. GNNs automatically give us high order neighborhoods, but are not inductive for unseen graphs for the moment. There are some examples at Chevinet, but not in general. So one of the first example of diffusive rewiring is the GDC or DGIL method, which is based on a page rank or personalized page rank or heat kernel. And the idea is to change the input adjacency matrix of the input graph. This is done once because we are dealing mainly in this part of rewiring with the problem of node classification, and then use the weights of the diffusion as alternative weights for the message passing. So there are 2 examples in this method. All of them are parameterized. The personal page rank depends on the parameter alpha. And what we do is to recompute the diffusion matrix, and we have to learn which is the optimal alpha. And after that, we threshold this matrix and recover the edges. And this equivalently can be done with the heat kernel. And in this case, the parameter have to learn what's the best time, providing the best, the optimal time, providing the best, the more informative diffusion for the task. So, well, this S has a form of an inverse and is a stochastic matrix. And in practice, what happens is that diffusion works as low-pass filters for structural noise. So we can use, for instance, a transition matrix, the random walker, and the interpretation of T to K is the probability of hitting J from Y in K steps. And when K increases, the hitting probability is proportional to degree, because of the fixed point of the mixing time of the random walk. But more distance nodes can be reached. This is called the structural smoothing. So we have example here. We can find these examples in the notebook. So we have a block model, which is very toy model, and we can see the structural noise with as white pixels here, and in the center. And the idea is to remove all these white pixels using diffusion. And well, it is important to see that depending on the transition matrix we use, we will have self loops here. The page rank, personalized page rank, has the property that the teleporting drives you to the origin of the random walk. So while this matrix is smoother than the original one, but it is more interesting than the original one, what were we gaining or not with that? Well, this is important to note that with having S, we can threshold a little bit this S, which is called sparsify, that is to preserve all diffusions greater than a given epsilon. And we can do that because personalized space rank are particularly interesting for doing that. This is due to a property called localization. That is, the transition probabilities, the state vectors are often very sparse. And well, if you specify the original matrix or the diffusion matrix, we have that the eigenvectors, eigenvalues, sorry, are not affected. Especially only affect the highest and the lowest eigenvalue, but not the intermediate eigenvalues. So what happens after the specification? So after the specification, what we have to do is just to compute for the specified matrix, compute again transition matrix. And in this transition matrix, once we have done this, we can explore what is the probability, the magnitude of the edges, which are intraclass, are interclass. So intraclass are the red ones. This is distribution of magnitudes at interclass. So sometimes we can find a good threshold. We can separate these two kind of edges, because what we want at the end of the day is to preserve the communities and to remove the cat. Well, not exactly, in this case, we are removing the cat in the example you have in the notebook, but in general, we will see later that the personalized page rank diffusive rewiring has a property that we cannot arbitrarily increase the bottleneck, which is going to be very important and critical for the task we are discussing today. In particular, this is measured. This bottleneck is measured by a quantity known as the Cheeger constant. The Cheeger constant comes from a separated problem. That given a graph, the idea is to remove as few edges as possible, to disconnect the graph into two parts and make a partition. But these parts has to have a most equal size. It is strongly related to the problem of finding the average gap. Again, solving the problem implies exploring exponential number of subsets of the graph, because each subset induces a partition. So the idea is that the Cheeger constant is going to be the minimum HS between all the partitions. So doing that is NP hard, of course. At HS, a particular HS is the ratio between the cat, which is the number of edges going from one partition to the other, divided by the minimum of the volumes, which is volume is the sum of degrees of the nodes in each partition. So this is the description of the cat. So what the interesting thing that although this Cheeger constant is very hard to calculate, we can use some spectral bounds discussed in the book of Fan Chang and other works, and we can have the Cheeger constant is upper bounded by the Fielder value. The Fielder value is getting very, very important in the rewiring literature. And vice versa, we can bound the Fielder value by the Cheeger constant. Well, the Cheeger constant is very related to the notion of curvature. In general, what we have is that curvature can be positive, negative, or zero. for instance, in real curvature in real functions, but in discrete geometry, the curvature quantifies the dispersion of geodesic. For instance, if we take the geodesic out of the shortest path, we can have that they have zero curvature because all geodesics shortest paths remain parallel, locally parallel to a given point. This is the grid. Well, the curvature is positive with the geodesics converge to a given point. This is the case of a click. Or it can be negative if we have a tree where there's a divergence of the geodesic. So all these three concepts are very important. And in the recent paper on topic at all, and edge curvature it's characterized by a discrete function, takes into account a number of triangles based at a given edge. We are talking about the curvature of a given edge. How curved is that edge? This is going to be related to the positive curvature. We have the fourth cycle based on the edge without diagonalizing sides, and this is going to contribute to zero curvature as it is happening in the grid. Or we can use also a quantity called gamma max, which is the maximal number of 4 cycles. So using this formula with concept, well, topic and all define what is called the Forman curvature, which the Ricci curvature is 0 if the minimum degree between in the edge is 1. But if it is not 1, this is quite curious that we have some here a quantity which is well, first of all, we have a quantity which is very negative, it's -2, and this quantity is going to be compensated by positive quantities. All the positive quantities are dedicated to make the curvature positive, as much positive as possible, because we have, again, if we come back to the tree, if we are focused on our negative curvature, we will have that all these nodes will collapse the information and we have an over-squashing problem. So we want to be far away from this configuration. And if we want to do that, we have to use these other quantities to be far away from the negative curvature. So the particular interesting that this 1 divided by the degree of the first node to the edge and plus the inverse of the second degree of the edge is called, we call that a local resistance. It's a relationship between the resistance or the commute time and the curvature. We take into account the number of triangles, maximum and minimum, and the number of squares or cycles based on a given edge. So, well, you can, for this case, for the edge 0, 1, we can see that this curvature is a little bit negative, not too much, but this is indicating that if we remove some of these edges, this could lead to a kind of bottleneck. But we are we are close to that, but not too much at the moment. But if we remove this edge, what happens is that this 0, 1 edges is not critical. So because it's belonging to one of the communities. So we are going to have a positive curvature because the geodesics are going to converge. But if we keep removing things here, what happens is that we have a strong bottleneck because this edge becomes very critical, and we can't remove this edge without damaging the global structure of the graph. So in the paper of topic at all, they say that edges with a very negative curvature create bottlenecks, and this is why the reason I explained before. And what happens with a bottleneck? So we have this original graph, and we tried to diffuse information, and the bottleneck is making pass this information, communicate this community and this community only through this edge, and this leads to a misclassification. One community, the dominant class in each community, is absorbing the other. But if we enlarge the bottleneck, what happens is that the number of misclassification decreases. It's only associated with this kind of nodes. This is the aim of the algorithm called stochastic discrete Ricci flow algorithm, which basically is doing the following steps. For each edge, we take the edges with minimal Ricci curvature because are the edges we are more critical for the graph. For instance, this edge is very critical. And for every other edge, we compute a vector quantifying the how is improved the Ricci curvature, how is improved in terms of being positive, and then we sample indexes of k and l for neighboring edges with probability proportional with this tau parameter, which is a parameter of the model. We have to learn this model or this parameter, and after that we can remove the edges with maximal Ricci curvature. And then what we can do is that for this case, what we do is to enrich a little bit the bottleneck, and after that we can remove some of the edges we typically are in maximal curvature. They are inside the communities and not in the bottleneck. There are two questions here, and the most important for instance, in the notebook, you will find that you have to use CUDA, especially the grid instruction, to compute all the Ricci curvatures because they are not differentiable. This formula is not differentiable, and you cannot learn that curvature. And later on, we have to know also the tau parameter, and we remove edges with maximal Ricci curvature with respect to a given threshold. So we have two parameters there to learn or to set. But what is important is that all edges are a Ricci curvature greater than k. So what happens is that we increase significantly the bottleneck, which is very important because especially in heterogeneous cases that is heterophilic graphs. Well, what is the difference between these two approaches is that diffusion works a low-pass filter. So we try to do is to remove the structural noise. And what is doing the Ricci flow is a kind of chirurgical on behalf of the structural test of each edge. So we have to just do some local work in the critical edges and try to reach the bottleneck. So it is important that this property is very important because the Jigger constant of the diffusion can grow not arbitrarily, but because it's limited by the Jigger constant of the Ricci flow. So we have to take that into account. In addition, SRDF preserves more the structure than the diffusion, because in particular in the notebook, you will see that we end up removing the cut. So we can see that here. So after the SRDF, what happens is that we get this new graph, which is the rewired graph. You cannot recognize the difference between this and the original graph. But if we take the difference between the two graphs, we see that in blue we have the removed edges, which are typically intra-community, and the new edges are typically inter-community. And if we compare the degree distributions of the graphs before and after rewiring, we have that with the SDRF method, they are similar, but the other method, the diffusion method, tends to produce a different degree distribution. Concerning the results, it turns out that diffusion works better in homophilic graphs, because what we are doing is typically we even can remove the cut, but it's working better in homophilic graphs, which happens here in Cornell or Texas or here, and well, for instance, here in Cora, so the digital is working better. Cora, CiteSeer, and PubMed. This is the degree of homophily. So talking about inductive rewiring. So first of all, we're going to talk about some important bound, which is vertebrating in some way work on rewiring using commute times. This is called the lowest bound. The lowest bound explains how expressive are commute times. So basically, the lowest bound has two parts. In this part, we have the deviation. This is called this 1 divided by du plus 1 divided by dv is what I called before the local resistance, which is if you remember this in the formula of the Foreman curvature. Well, for the commute time divided by the volume is called the resistance. So the resistance should be, which is the global resistance, should be far from the local resistance to be informative. Otherwise, if these two quantities are very close, our distance is just 1 divided by du plus 1 divided by dv. So it is not just depending on the degrees of the origin and the destination. But this happens if the spectral gap is high, because if you have a small spectral gap, so what we do, okay, so 1 divided by this small spectral gap is going to be large. We have small spectral gaps, so this is an error here. It's going to be informative. If the spectral gap is large, it's going to be not informative. So there, this bound was later, after the proposal, was revisited by Volux al. Well, they had a paper called "High Probability of Getting Lost in Some Large Graph." When we have large graph, what happens is that, well, the minimum degree increases, the probability of having a very large bottleneck increases as well, because we have connections between two communities. And well, what happens is that the local resistance is close to the effective resistance, and then this is not informative. However, this is only happening this from 2014. In that days, the most interesting graphs were for instance, the GNN graph, or some related graphs of proximity graphs. And in these cases, this happens because the bottleneck was very large. But when we have internet graphs or real world graphs, many of them has a very small gap. But this small gap can be bad for the problem of the bottleneck, but it can be good for the estimation of the commute time, which is something which is interesting. So we can also talk that the effective resistance are related to the pseudo inverse of the Laplacian and or the Green's function of the graph. And this is important also for people that is using the shortest path at positional encoder or something like that. Effective resistance are upper bounded by the shortest path. So if the effective resistance between two nodes is a given quantity, this quantity is smaller or equal than the shortest path between these two nodes. But what happens with the effective resistance or commute times, we talk, we don't distinguish between them, informally talking, is that effective resistance are by far more informative about the role of the edge in a graph, since all paths are considered for computing the effective resistance. So we will see that we have a very high effective resistance, a very low curvature edges that are connecting bottlenecks. So, well, this is important. What is the impact of the lowest bound? So this is important when you have a network to investigate what is the bottleneck of the network, or of the kind of networks you have at hand, because it's not the same having an SBM, which is a stochastic block model, which is a couple of communities with a small gap, 0.02, or having a bottleneck with one order of magnitude. This is the same graph with virtually the same class of graph having 0.75 quantity, which is, we have, is quite relevant. The colors are because we map the fielder vector as node attributes. The idea of doing that is to explain how the elements of the fielder vector are distributed when we have a small gap or when we have a large gap. So this is what we have here. So the spectral gap, we have to reformulate that the spectral gap is the Dirichlet energy of the fielder vector. This is important because it's a quantity, is the energy of this special vector. We've solved the normalized cut problem or the average cut. And this spectral gap is controlling the variance of this fielder vector, and consequently is controlling the scattering of in the latent space. For instance, here you can see that when in the first SVM have a small gap, we have that the community, the blue community and the red community is very far away. This is what happens here. The blue community and the red community are far away, but in the other graph where you have a larger gap, what happens is that the communities can be even overlapped. So in addition, if we look at the latent space of the first graph, here we map each node. The strength of the color is the degree. So nodes of high degree are clustered together in the latent space of the commute time embedding, and you can see that in these curves, in these level curves. But in the other graph, they are confused. So you have this kind of distribution of KDE, just improving the bottleneck by means of one order of magnitude. So one order of magnitude is critical for differentiating between one bottleneck and the other bottleneck for the same type of graph. Well, effective resistance is very informative, but it's also useful because it reveals the impact of each edge in the topology of the graph. To visualize this better, we use a theorem of Spilner-Srivastava, which is the sampling theorem, which basically says that if we take n log n samples, well, n log n divided by epsilon samples, where the probability of sampling a given edge is proportional to the resistance of this edge, what we have is that my original, the Dirichlet energies of the original graph are bounded by the Dirichlet energies of the modified graph, or the modified graph is bounded by the Dirichlet energy of the original graph. And well, the factor is depending on epsilon, of course. So this is very important because if the Dirichlet energies are contained, are bounded, this means that the eigenvalues are bounded. And this means that the original graph is close to the sparsified graph. So this is a sparsified version of the previous graph here. When you can see that basically what it's doing is to the sparsification or the commute time is to remove intra-class edges and preserve mainly the interclass edges. Well, this is not so obvious when you look at the second graph where the spectral gap is higher. And you can see this is important because here we put we represent the KDA of the probabilities, and in red we have the probability of associated with the edges, probability of sampling an edge in the first graph, and they are quite separated. But this in green we have the probability of sampling edges in the second graph, which are overlap at basically are the same Gaussian-like distribution. So this is important to take into account that the bottleneck is controlling how separated or overlap are these distributions. In addition, many ways of increasing, for instance, formally increasing the bottleneck when we need to do that, they rely on a notion called expanders, and expanders, what they do is to enlarge a little bit these limits. Another interesting fact coming from the commute time embeddings is that the commute times relies on downscale version of the eigenvectors. For instance, the commute time embedding is given by the distance, the Euclidean distance between the two vectors in the latent space. This is coming from this this formula Edwin explained before. But if you look at this formula, and these are the columns, and you look, one of these columns has this shape, is the square root of the volume, and then 0, the first non-trivial eigenvector divided downscale by the Fiedler value, the second, and so on. So this means that in the transpose of the embedding, not in the embedding itself, but in the transpose, what we have is the spectrum, well, the spectrum, sorry, the eigenvectors scaled by the eigenvalues. So here you have the transpose. Look at the first dimension. It's clearly in the first dimension we divide. This is the Fiedler vector. We divide between, this is for the first graph. We divide between the blue and the red nodes. But we take the difference between the scale eigenvectors and the usual eigenvectors. We have that the error, independent of the type of cut, has this shape, is decays, and is close to 0. So it depends on how good or bad is the Fiedler vector, the Fiedler value, sorry. But this is important that we can use this transpose to interpret or to understand or even to propose new methods or new approaches to directional graph networks. So here I put one of the figures in the paper. What they do is to get the original graph and map the color. Well, the color depends of the value of the eigenvector, and then you use the computed gradient, and then they use that for improving the diffusion process. But look at this case. All these things have to be pre-compute, but of course, you have to do that if we do that spectrally. But as we will see later in the next section, if we can learn these embeddings, we can remove all this step here. Or basically, what we can do is make inductive the directional graph networks. So now the term is of Adrian, which is going to talk to you about how to learn that commute times embeddings.
Thank you very much, Francisco, for your explanation of the transductive rewiring and the prior work here. So yes, just a quick recap. We have seen like how to perform rewiring in a couple of ways that are principles, such as diffusive and using curvature. We have also mentioned a family of graph structure learning methods. And we have learned which is the commute times embedding. I mean, this is the recap of the commute times embedding. We have seen that it's the expected time from go to E and B and come back. There's an embedding which Euclidean distance is the embedding. It has relationships with the eigenvectors because in the computation are the scale difference, square difference of the eigenvectors, also with the pseudo inverse of the Laplacian, that they can be calculated also using doing an optimization problem. And they are very informative because they have this direct relationship with the eigenvectors, as we have recently said, with the Dirichlet energies as well, with the expanders and sparsifiers, and also with the Chigger constant and curvature that we will see. So this slide is just the quick recap of why we are using commute times for rewiring, because it's very informative. So we are going to present city layer. City layer is a GNN layer that literally learns this commute times embedding, and then you can use it for performing rewiring, for example. So we have seen that you can calculate it spectrally or in an optimization problem. So our main contribution is translate that optimization problem into a differentiable function. So we have this trace here that is the same trace here, and the orthogonality restriction we have moved like to this term here in the second term. So once we have this loss, we can literally build a GNN layer. And this GNN layer, what it has is it maps the feature space to the commute times embedding. This MLP is like one layer of a couple of layers MLP with an hyperbolic tangential activation function that it's going to learn with the aforementioned loss function, okay? And once we have the embedding, you can compute just the Euclidean distance of that embedding divided by the volume. So you have the effective resistances and you have the commute times distance matrix. And when you have this commute times distance matrix, in our experiments, we have used this as the new adjacency matrix for new layer, but you can use it in the way you prefer. And it's also interesting that you can use it as the first layer, but you also can use it as the third layer or whatever, because it's just like another layer. It's pulling from the feature space to the commute times space. So we are going to be looking at these two terms that are the important ones, the commute times embedding and the commute times distance, especially in this layer. We have already seen theoretically what it is. And if you see this layer, the thing is that it's as simple as this layer. It's an MLP that learns with that loss function. And you can use then this commute times embedding for using it as a adjacency matrix, as we have made in our experiments. You can use it as edge feature. That there's a paper that's affinity aware that they use it is, I think it's cited in the previous slide. Sorry, should be cited here, but it's cited in the presentation. Or you can use it these features because it's a node embedding as a node feature as a positional encoding. But with the difference that the position encoding is learned rather than pre-compute. So we can go like step by step, watching the code. Now, after I explain the city layer, we will go to Colab and run a couple of things so you can see especially how it works. But first, we can see that it's simple. For defining this commute times embedding, the only thing you define is a linear function where the number of centers is O ordered n, and you have this, which is the commute times embedding. Once you have the commute times embedding, that in our code is S, what we compute here is this. We do the Euclidean distance of the embedding, we calculate the degree for getting the volume of the graph, and we just have the commute times distance is divided by the volume of the graph. And then we mask it because for graph classification, we are masking it. So we are not adding new edges, but we are kind of sparsifying the graph and prioritizing edges. But for node classification, you can remove that part and new edges will become to the graph. And then the loss functions are also quite straightforward to understand. You get your Laplacian matrix, and then you do this formula here, you divide it, and you get the mean over the batch, and you have the orthogonality restriction as well. I mean, you can see that here for the paper, we have implemented it in a denser way, but we are also working on doing it in a sparse way, so it's more efficient, and we can integrate it into PyTorch geometric as well. So if we audit this layer, we are going to be auditing this layer for seeing how this layer really learns the commute times embedding, on how is this layer learning, because maybe there is going to other local optimums. So for example, we have this graph that is a graph from Colab, from the test set of Colab. And this first step, this embedding is going to be this embedding, okay? This is the spectral computed one for this same graph. And as we can see here, like respect more the distances, but the structural role is not like perfectly gotten by the city spectral city, but our city layer learns this embedding. Okay, as we can see here, I mean, we are still doing a lot of experiments to debugging the layer and understanding what it really, why are these difference here between the two embeddings. But the thing is that it compacts in a more dense way the same communities here rather than here. So but that's up to some point it's learning like similar things, and obviously this is a TSNE projection, so it's also depending on that. And once we have this city layer, as we have said, like the city distance is this city embedding, the city distance is the Euclidean distance between these embeddings. So just we calculate these formulas we have seen before, and here's very interesting what happens in the spectral commute times distances. The commute times distances between these embeddings are a kind of normal distribution. So you can think of this as if you have a budget to put in every edge. You can put a budget, you can put a weight on every edge, and the edges with more weight are going to be the ones in the bottleneck. But here, let's see that you sparse the budget in a more normal way, rather than the one we learned, that it's literally, here we can see the order of the city distances, that most of the edges are going to have a very, very low distance. So most of the nodes are going to be very close. So we can see here that it compacts all of these nodes. Maybe that's all the reason why we have very few, I mean, a lot of edges with very few weight. But in the other hand, it gives a lot of weight to some of the edges, as these edges are going to be the edges of the bottleneck. So it's going to prioritize the bottleneck rather than the communities. And I mean, it's very understandable looking the city embedding. So once we have audited all the layer, we can see how it works. So this is the original graph, and what city layer does is it sparsifies the communities and gives more importance to the edges that goes from the communities to the bottlenecks that are these ones around here. Yes, and the main idea is that we have performed graph classification with a bunch of benchmarks and with a bunch of other methods. These are the, I mean, it's like a proof of concept. So we have used like very easy GNNs. The normal is just the classical graph classification pipeline with a min-cut layer, that it's a graph pooling layer. And here for the city layer, what we have done is just we have put this here for using the commute times distance as the new adjacency matrix. Here, it's important to notice that we are not using the commute times embedding as a new feature. We are just using the commute times distance as a new adjacency matrix. Okay, we can see here that especially in the graphs that are related with social networks, these kind of graphs that has hubs, power law degree scales, it increases the average performance. Okay, and especially the ones that doesn't have features. Then when you have graphs that are related with proteins, with more chemicals, the increment is not that big, and it's at the same order. It's also important to notice that these two graphs has features, and it's known that when a graph has features, it can override the information of the structure, and then here a simple GNN rewiring works as well as all the other methods. Yeah, and finally, we have two synthetic datasets just to realize that when you have a spectral gap that it's very low, here commute time is working better than all the others. And another important fact is for DGIL and SDRF, as we have seen, there are preprocessing methods with parameters, or for no classification, they do hyperparameter search, but it's intractable doing it for graph classification. So we have used the standard parameters in their papers, and that's the reason. And why it works better for graph classification, as we have seen in the introduction, when you use spectral metrics for graph classification, your GNN becomes more expressive. and we can see it here in the graph readout. Okay, its dot is a graph. So it's dot is a graph from the I'm collab dataset or MDMB. It's in the paper, and we can see here that for the baseline, the latent space is very compact. There's a lack of expressiveness. It's not able to really differentiate most of the graphs, but the latent space of the city layer is more sparse, so means that it's able to better detect the difference between graphs. Okay. So now we are gonna change to collab. So this code is this last notebook. As we have said, you have a lot of notebooks just that are the other parts that are implicit code of this tutorial, but this is gonna be more explicit. You can run it in the collab. So let's start connecting to the runtime. Yes, we have to install a couple of things. First of all, SciPy, because there are some incompatibilities with between NetworkX and SciPy, Torch, and then we clone the GitHub tutorial to be able to work here to have here all of our code. But we can just, while this is starting, we can go and we can see. All right. Okay, let's do it. Let's see the code with the graph classification. Okay. What we are gonna be looking at, the first thing is like the city layer that we have seen in the slides, which is this layer. If you want to use it, it's as simple as importing this in your, when you clone the Rewire repository. But we are gonna be here defining the layer, I mean, explicitly, so we can look what this layer does. Okay. So the thing is that this layer, which is this layer, we have implemented in a way that we are gonna be implementing in that place. Okay, set is set. So this S is just the pooling with a linear layer. Okay, from your layer. I mean, maybe it's better to just define. Sorry, maybe it's better to just define the network that we're gonna use. That it's linear, city layer, convolutional, min cut, etc. So this is the net. We define the convolutional layers, conv1 and conv2. We define the pool one. Pool one is this layer, and pool two is the other linear. And we have defining these linear layers. Okay, so first of all, as we have said, the implementation is dense so far. So we get the dense versions of the thing of the adjacency matrix and the feature matrix and the masking for the batch. Here we have a first linear MLP just for changing the features to other feature space, and then we perform the commute time rewiring. How we do it? First, we have this pooling layer, which is going to be the first pooling thing. And then we use the density rewiring, which we pass the features, the pooling, which is the city embedding, the adjacency matrix, the original one, and the mask. So let's see a look of what we are doing here. We are doing here is just we receive the city embedding. So if you want to use the city embedding, just you get the other thing and this S in your layer, and you can do whatever you want with it. Use it as a positional encoding, use it for a transformer, whatever you want. So we unsqueeze, we get the same thing. We use a tangential hyperbolic, as we have seen here, which is tangential hyperbolic. First, we compute the commute times distance, which is the Euclidean distance divided by the volume. And we mask it here for graph classification, okay? And then we calculate the losses. We calculate the Laplacian because we have already calculated the degree here. We calculate the numerator and the denominator, which is these parts of here. We calculate the orthogonality, which are these parts of here. And we return the new adjacency, the commute times loss, and the orthogonality loss, okay? Here is up to your imagination to use different losses or to use this commute time for other purposes. Okay, so that's the idea. And as we know, once here, we have made this commute time rewiring, okay? Yeah, I repeat that this is the commute times embedding, but here we are not using it for graph classification, but you can use it for your tasks. So once we have the new adjacency, we just use the commute times distance, which is this as the new adjacency for this new message passing convolutional layer. And then we just do a graph pooling using min-cut pool, which is a very nice paper as well. And yes, we do the readout and the relu and MLT, okay, and the losses. I don't know if it has already, yes, has already. So we can run it, we can run our layer, we can run the net that uses our layer. Remember that this layer is in the code, so you don't have to explicitly write off this code, it's already done. We run the train and test. We can run the data sets here. I mean, as we are a bit running out of time, we are not gonna literally train the model here, but you can do it. This notebook is public. So you load the data set, you make the splits like in an stratified way or in the default way by Python geometric, and then you can create your model and you can train it, okay? But we are going to be auditing the layer, which means that we are going to get the commute times embedding and the commute times distances. So you can run this without training this code, because in the deep wire, there are a bunch of already trained models. So we learned the data set. We are doing it with IMDb binary because it's the smallest one. So we can do it more quickly, but you can do it with Colab or with Reddit, that the models are in the same folder as this. So we load the model, we get the connected graph just for a fair comparison with the spectral version. We get the train path of this model. If you go to this folder here, you can look more models. Here we are using the same CityNet as we have said before, but we are just saving the city embedding and the unique adjacency, okay? Just for watching. You have see here the city embedding, we have it here, and the new adjacency, we save it here, as we have said before. So we import the train model. Let's wait for our train model. We test our train model with the dataset just for checking that has been correctly, okay, has similar classification as in the paper. So yes, for the city rewiring, okay, we select a graph, the one that you prefer from the list of connected graph, or just one from the dataset, okay? Just use here just a bunch of them that are interesting, that clearly structure, and then there are complete graphs. That is also a very curious way to see. So we select a graph, we predict the new adjacency. So we take the graph, we put it to the device, we pass the graph, the individual graph in the model, and we get the new rewired adjacency as the new adjacency that we have saved it. And then just we visualize the graph. And here, okay, this is the original graph. This is the commute times distance. And this is just a normalization of the commute times distance, but here you can do whatever normalization. So if you want to use other graph, just check it, just use the 17, for example, and you can just run it again. Okay, this is a similar graph, but okay, yes, and that's the point. And for the commute time embedding, it's the same. Okay, from the same model that we have previously loaded. We check, we get the graph again. We get the degree just for, and the spectral commute times just for comparison. And we get the learn commute time embedding, the same. We pass the graph to the model, and we get the learn commute time embedding as this variable that it's inside the model predefined, and we plot it up there. And yes, we can see here like the same, that the spectral CTE respects more the position of the let's say the coordinates, and rather the learn CTE respects more the structural role of the thing. But I mean, this is the way that you can use it. And yes, we are planning to improve a better implementation for putting PyTorch geometric. So yeah, you have the code there. And okay, let's continue with a couple of things about the city layer. Okay, you can see it here. Okay, expressiveness. Whatever doubts that you have with the code, just write it on Slack, on Telegram, reach out with the email, Twitter, whatever you want. What? Twitter. Okay, perfect. Yeah, Twitter as well. Here we are gonna do the relationship between the city layer and some important concepts as the checker constant. So we have already seen that the checker constant is like a problem that it tries to find the minimal cut for separating two communities. So the checker constant, the upper part are the edges of the bottleneck, and the lower part are the volume of the community. So our city layer, what it really does, I mean, the commute time, what it does is like giving priority to the edges of the bottleneck. So it's gonna kind of maintain this set, the size of this set over here, while sparsifying the communities. So empirically, it could be seen as at least as we maintain the checker constant, or rather in this empirical way, we are kind of reducing we can making the checker constant a bit bigger, but it's not only, we can not only see it empirically and by the intuition. In Aleph et al, there is a couple of theorems that relates the commute times or the resistance distance, as we have said, with the checker constant. If we see here the edges in the bottle, the diameter resistance of the graph as the maximal resistance, which, as we have said, are the edges of the bottleneck. We can see that the checker constant is upper bounded by the inverse of the proportional of the inverse of the resistance. So the thing is that when we are choosing the edges with the commute times, you choose the edges with more resistance. So you are never making this upper bound like more tight. So we are maintaining the upper bound. So the thing is that you when you rewire using city layer, you do community stratification of preserving the bottleneck, and you preserve the diameter resistance in the new graph. So at least there are no reduction of the North theoretical reduction of the upper bound of the checker constant. Okay, and this gives us like an intuition that we can perform rewiring in a chirurgical way. Let's say we calculate the commute times of the edges, and as the curvature work that we have already explained, we can loop over the we can make a different loops, choose the one with more resistance, put it in the graph, and that's it. So we can do it in a chirurgical way. And the relation with curvature is not only that, but it's also theoretical and explained by the Brenil-Lambriot. In the Brenil-Lambriot, there is a paper from this year that they have explained two theorems with the relationship of the curvature, the node curve and the curvature and the commute times. Okay, these can see as the learned commute times. The nodes are going to be related with the curve, with the commute times distances as this, like a summatory of the neighborhood resistances of the edges, and then the edge curvature is just this. So if we compute this in the, okay, I'm not using the laser. I'm using the laser. If we compute this in the graph, here's the original graph. Here is the graph rewired, but our city layer, okay? And here is the curvature calculated from the learned city distance, okay? So we can see here that there is a correspondence. Also, this is a bit more symmetrical rather for these normalizations. That's why here are different weights and here are the same weights. Yeah, and that's it. And city layer can be seen as a differential or curvature way. So this is also the visualization where you can see the relationship with the commute times embedding, that if you plot the commute times embedding as a KDE plot, you have the curvature of the graph. If it's more complete, you have a round. If it has the bottleneck, it's more curvy here. We have also performed node classification experiments we have made two models, as we have said. You can use the set as positional encoding, or you can use the adjacency as city layer. Sorry, you can use the city distance as adjacency. Both of them are learned, okay? So we can see here that commute times embedding helps, as a positional encoding helps in some homophily task, and commute times embedding, commute times distance helps in heterophilic task, okay? Here we don't mask the adjacency, as you can see here. So it's also like kind of a full commute time distance attention. And these are just the nodes, the node embeddings that you can be that here is more sparse. There are 3 classes that it can differentiate. Here is less sparse. Yeah, and finalizing this inductive rewiring, the last part is the spectral derivatives. We have also proposed another layer, which is based on reducing the spectral gap. Maybe you for some tasks, you really need to reduce your spectral gap to minimize the spectral gap. So the thing is that the filter value is the spectral gap of your graph, and you have, and if you define this loss as getting the a similar graph as the original one, but minimizing the gap, like making this like narrower, you have you can compute this, and you have the gradients. You have the gradients here. And the main thing of this gradient is that you have to calculate the filter value and the filter vector. Obviously, this filter value and this filter vector, if you have to compute it spectrally, is very costly. But we can see the filter vector, as we have seen along all the presentation and the tutorial, as the node membership of 2 clusters. And again, values are the Dirichlet energies. So we can just use a similar schema as the city layer, but for learning both of these values. So what we are learning here is just the mapping of the features into 2 clusters. That, as we have seen here, is like kind of approximation of the filter vector, okay? But here, if you use a sigmoid, you don't know what are going to be these values. But in Hong et al., they say that the approximation is that the filter value gets this value when the node belongs to the one cluster, and this value when it belongs to the other. So we just do this pooling into 2 clusters, do this approximation. If it's in the first cluster, this value and this value, and then we compute the Dirichlet energies of this approximated filter vector. So we now have the filter value, the approximated learned filter value, and the learned filter vector, so we can compute this derivative in a more efficient way. And this is how it performs the rewiring. Okay, we can see here how it really reduces the size of the bottleneck. It almost disconnects the graph, while it leaves the communities mostly untouched. So we can see that both gap layer and city layer are perform different objectives. Okay, and it's a very, it's a very interesting method. So whatever is your goal, you can just use it, or city layer or gap layer. If you wanna disconnect the communities, use gap layer, the other way around. And it also has a very good performance in graph classification. It allows to disconnect to better differentiate the graphs, okay? And just finalizing the rewiring part, the future work, it's up to your imagination, but we have been recently discussing in the Slack that maybe not only editing the edges could be the way, but also editing the message function direction, or editing the full graph. So as Petar says, is augmented message passing. We also can see dynamic rewiring, in which we don't only rewire with respect to the structure, but also with respect to the homophily and heterophilia and utility. As we have seen here, the diffusive rewiring, the curvature, and also the inductive rewiring with diff wire, the commute times rewiring, are only related with the structure, okay? So maybe if you have to do node classification and you have a lot of homophilia or heterophilia, you want to do a rewiring that also dynamically adapts to that task, okay? And from our point of view, it always has to be more interpretable, because then there are also works that they use transformers for a full attention, but it's not very interpretable or efficiently, computationally speaking. And in terms of the deep wire, you can use these learned CT distances or CT embedding for positional encoding, for directional graph networks, for Laplacian, whatever you want to say. I remember right now that yesterday the first oral presentation was a paper that they weighted the embeddings using the eigenvalues of the Laplacian, so maybe it's also another thing. And also the code is going to be more easy to, it's going to be modified for being more easy to use and being more efficient. So that's all about graph rewiring, theoretically graph rewiring. Now we are going to talk about, I think it's a very exciting applications, because graphs are everywhere, but this is a human classical type of data. So most of the benchmarks of graph classifications are related with social networks. Also, most of them are related with proteins or whatever, but we are going to focus on the ones related with social networks, in which the node usually is a person. So yeah, this is the last part before the panel. So first, we are going to define which is algorithmic fairness, because maybe some of you are not very familiar with the topic. The thing is that machine learning, as all of us know, is very related. It's being used for critical decision making, for making decisions in critical scenarios such as education, job hiring, healthcare, in justice as well, and in justice. And when you are making decisions about humans in these high critical scenarios, you have to take into account a lot of ethical challenges, like the privacy, transparency, autonomy, but fairness is all of them, which is fairness is that the algorithms must not discriminate to anyone, okay? But why the algorithms are discriminate? We know that we are in a constant loop with the model, the individuals, the world. We, the humans, we define the data, and the model learns on this data, and with the model, with the actions on the individual that defines the world. So if some actor in this loop is biased, then the model is going to take biased decision, and it's going to be worse, because if the model takes biased decision, it's going to be more bias in the loop. And these social decisions has catastrophic consequences, such as loss of opportunity, economic loss, social stigmatization. So yes, first of all, algorithmic fairness is a big topic, and there are a lot of branches. But here, just for focusing and being concrete on what is graph fairness working on, we are only going to define group fairness and individual fairness, okay? There are a lot of bunch of definitions, like causal fairness, but here, just for explaining only the thing about graphs, we are only gonna get the hints of group fairness and individual fairness, okay? Group fairness is basically that our model should treat all individuals equally, independent of the sensitive attributes. So the idea is that the model does not perform systematically failures against one demographic group, okay? And there are different bands of metrics. We are gonna be putting a lot of formulas, so you have this tutorial as a toolbox, but we are not gonna be deepening on them, because we are a bit running out of time. But the main idea is that there are different ones, and you can define it as you have to have the different true positive rate or false positive rate among all demographic groups, okay? Among, for example, women and men, or whatever. So the error is equal for both groups. The predictive parity is equal for both groups. So the idea is that decision is independent on the protected attribute given the real level, or the other way around, that the real level is independent on the sensitive attribute given the prediction here, okay? We are gonna define the sensitive attribute as S along all the slides, okay? And then we have individual fairness, that is treat similar individuals in a similar way, that it's very related with the Lipschitz continuity, that if 2 points are close in the original space, in the data space, has to be close in the decision space. But why graph fairness? That's the main point of here. And I really wanted you to get to the point. The thing is that I want to go a bit deeper in just homophilia and heterophilia in between sensitive attributes, okay? So the idea is that we have a graph defined in the society by social relationships, for example, and in these social relationships, there are going to be overrepresenting homophilic edges due to social stratification or social homophilia, because we as humans, we tend to connect with people that are similar to us. But it also means that are going to be missing heterophilic edges that would have been present in a more fair world, that would have been present in a more fair situation. So, and this biased structure is a problem, because here, this is from edits from this paper that from Yushin Dong. If your attribute is biased and you have the structure not biased, when you perform message passing, you still have a bias. But the important thing is that if your attributes are not biased, if there's no correlation between the node attributes, the person attributes, and the sensitive attribute, and your structure is biased, once you do message passing, your latent space is going to be biased. And this is it's a synthetic example, but this happens in the real world. This is a network about friendship among students in Dutch school. The visualization is from this paper, but the dataset is they cite in the paper, and this happens in the real world. Here are all the girls and here are all the boys. And the consequences in the real world, when you're making decision on the nodes, if you make decisions in a fair topology, for example, for giving credit to people, here for this node, you would say that you would give the credit to this guy because it's mostly connected with people that has the same level as him. And this is a fair topology because there's no correlation between the structure and the sensitive attribute. In the other hand, if your topology is biased, even with the same attributes, you can see that all the nodes has the same attributes. Now you're gonna classify this node as you're not gonna give the credit to this node, okay? So this is a problem that if the connections are biased, if you just relate to other people because homophily things are not because of your level, you can have this kind of behavior. Also in recommender system, Francesco Harry will talk about that in the panel, but you can just, for example, as a recommendation of job, you can do biased job recommendations, but you can also create filter bubbles and echo chambers if you recommend the links that are very similar to you. So when you are recommending it in a loop, you can create these loops and polarize the society. And finally, in influence maximization, if there are influencers that have a big role in the society, they are going to tend to monopolize the ideas, or they are going to tend to monopolize the attributes or of the ones connected to it. And if this network is biased, then the influence is going to be biased, okay? So, I mean, this is the most important slide that I would like you to take. So usually in graphs, we have the graph topology, and in classical GNNs, we have the node labels. And this is the correlation between these is called homophilia heterophilia. Now we have an actor that it's the sensitive attribute. And the correlation between these distributions are going to be the biased topology. But there's also other connection here that is going to be the algorithmic fairness, the classical independence between the attribute and the node labels. So we are adding one more ingredient to the algorithmic fairness. Or we are adding one more ingredient to the GNNs, as you can see. And we have graph fairness that is analyzing the joint distribution between all of these guys. And so the main idea, for example, there are in this joint distribution, we are going to look, for example, these are unbiased attributes. The green node has 3 against 2, and the blue node has 2 against 2. and the relations are not related with the connected attributes, with the sensitive attributes. However, here, using the same things, the connections are related with the sensitive attribute, and here it's a problem because we are going to have bad accuracy and biased decisions. So here it's a problem of heterophily in the labels and homophily in the sensitive attribute. We can have the other way around, that is not correlated, the structure is not correlated with the structure is not correlated with the sensitive attribute, but the attributes are correlated with the label. So here we have heterophily in sensitive attributes and somehow homophily or whatever you're gonna do it. Here, usually the graph here is useless. And then you have the worst case scenario, that it's when everything is biased, that you don't know if I mean, your decisions are gonna be perfect, but it's gonna be very biased, the decision. And then we can have a lot of taxonomy ideas. We can define fairness definition for different tags and use it with different techniques. But you're gonna define the last 5 minutes. We are gonna look the graph fairness metrics, which are node fairness, which are focused on the decisions, and structural fairness, so focused on the structure segregation. So for node fairness, we have group node fairness, which are basically that the node prediction is independent on the sensitive attribute. We have individual node fairness, which we are going to see that similar nodes will lead to similar predictions, and similar nodes is defined by some similarity in the attributes usually. Then structural fairness, we have group structural fairness, that basically is that the structure is independent on the sensitive attributes, that people doesn't build relationship according to the sensitive attributes. And then we have individual structural fairness, which means that similar nodes should be connected. Some similar, I mean, if we are similar, we should connect. That's it. But I want to see this from a pipeline point of view, okay? Yes, this is the pipeline point of view. Remember, this is blue and this is green. We have the topology and we have metrics to measure the fairness in the topology, such as the attribute assortativity. Then we do fair representation learning, and we can have metrics, individual and group, on the embeddings. Okay, we are not gonna go deep because we are gonna go focus in the rewiring. Then we perform classification, and we have group classification metrics and individual classification metrics. But we can also do clustering, and we also have both group classification and individual classification, and we are gonna do link prediction when we have group metrics and individual fairness metrics. All of these are fairness metrics, okay? As we can see here, these tags are more related with the structure. But the thing is that there are also a lot of applications, such as influence maximization or recommender system for rankings, okay? And we are going to focus in all of these. I leave you here this slide, so you have this as a toolbox with all the different metrics. But the main point is that you can perform graph rewiring here, and whatever you do here, it's gonna affect in cascade to all of the other tasks. So if you do fair graph rewiring, your embeddings are gonna be more fair, your predictions are gonna be more fair, your clustering are gonna be more fair, and your classification is gonna be more fair. So that's why we are gonna focus in the importance of the rewiring in fairness, because first of all, it's related with homophily and heterophilia, and second, whatever you do in the graph, it's gonna benefit to all the tasks, okay? So I'm just gonna explain 2 papers, okay? So we can finish like 5 minutes after, but just to get the idea. So this paper on information of fairness, they measured unfairness in this way. Their metric of unfairness is they have the adjacency matrix, they do the CAHOPs that we have already explained it in the theoretical part, but they choose the length of the cascade and this parameter, the importance of it. And then they do the distribution that it's literally the the distribution of all the weight of the edges intra-community 1, inter-community, and intra-community 2. So they do the CAHOPs, and then they get the the distribution of edge weights. They do all the pairwise distribution distances, and they get the maximum, and for them this is the distance, this is the unfairness. Why don't they use the assortativity or the homophily? Because, for example, here they explain it in the paper, these graphs have the same assortativity, same inter edges between sensitive groups, but the information unfairness is different because it's like kind of over squashing into between the two sensitive groups. Look here that they are not looking at the labels, okay? They are just performing sensitive group rewiring. And they propose this algorithm that they call max fair. They want to add new edges to minimize this metric, okay? And the problem is that this metric is not submodular. You can add one edge, the information unfairness doesn't improve. You can add one edge, the information unfairness doesn't improve or even decreases, yes, increases. And then you add one more and you fix everything. So they calculate the node attribute centrality that I leave you here the formulas, but the idea here that it's a GNN community is like doing a message passing with the one hot encoded sensitive attribute as feature, okay? It's literally what they do. And then they use this embedding of the node. Yes, they calculate again the distribution of all the weights of these classes, and they score it in this way, okay? And with this, they are defining that the edge with more score is the edge that is going to relieve the over squashing in that scenario. So this is one way to do rewiring. Other way that they do in bursting the Friedel bubble. There are two of the first papers. What they literally do is they do like limb prediction in the normal way. They do with tip walk and they do the limb prediction this way. And then they derive this formula that means that how flipping an edge predictions would change the modularity between the sensitive attributes, okay? The modularity is defined that way. So they score the edges, and the one that most changes the modularity of the sensitive attribute, they flip it. This paper also have a non-rewiring approach, but it's very famous. That's why I explain it. It's just an adversarial way of doing it. They predict the links, and in the other way, with the same embedding, they predict if each pair of nodes is intra-class or interclass, and they do an adversarial way. So this discriminator doesn't know anything about the class of the nodes, and this link predictor still works well. There are dyadic fairness, which is a very interesting paper. We are running out of time. I'm going to be very fast. They define dyadic fairness as that the probability of a link predictor to predict one edge, in where the nodes are from the same class, has to be equal to the probability of predicting an edge where the nodes are from the different class. And in this paper, they really derive a lot of metrics related with dyadic fairness, and also related with bounds that they propose in this metric. So what they do is they do projective gradient descent to get fair embeddings. So the idea is, first, they train some epochs, just maximizing the utility. They use variational graph autoencoders for link prediction. And then they train other epochs. In what they do is they have this fair loss, which means that the score of the intra edges has to be equal to the score of the inter edges, subject to they add new edges, and the new matrix that they do is row stochastic and is still like a random walk matrix. For doing that, they just compute the gradient of this function, and for being compliant with this restriction, what they do is they project this matrix to a feasible space. In the paper, they do a smart implementation of that. But you can do it in a more simple way. Fair draw from Spinelli et al., Simone Scardapane. What they do is they drop out homophilic edges with this probability, half plus delta, and they drop out heterophilic edges. So if you have delta as 0, you just do a random dropout, but here the red nodes are define the homophilic or the homophily of a node, okay, the sensitive attribute homophily. And if you increase delta, you reduce the homophilia of the nodes, okay? But this is not all. There are a lot of papers that do rewiring on fairness. We have explained this, and this, but there are more that they do individual fairness for link prediction, than they do individual fairness for representation learning, or group fairness for representation learning, they node classification, or even for specific applications such as recommender systems, because maybe these fairness definitions on graphs are very, very, let's say, context agnostic. And for example, rewiring dyadic fairness maybe is not always the best thing to do in a social way. So the thing is that what can we do now? Future work in graph fairness. First of all, a normalization of Bergmans, evaluation metrics, and pipelines. And we have seen in the pipeline, whatever you do in the graph, it's going to affect to all of the tasks. Whatever you do in the embeddings is going to affect classification, link prediction. And the papers, it's a bit of a mess because some of them, they do fairness in embeddings, and then they, sorry, they evaluate it with link prediction, or they do the same, but they evaluate it on node classification. So there should be a normalization on these Bergmans and evaluation metrics. There's also one important thing that graph fairness should be formalized. I mean, algorithmic fairness is formalized. There are there are like classical ways to define algorithmic fairness from a joint distribution point of view, and in graph fairness we don't have that. We don't have that definitions. We have just get the definitions of algorithmic fairness and start applying it on graph fairness, but we should think a bit more about it. We should go beyond dyadic fairness, because dyadic fairness is only relating connected edges, but the full structure, as we have said, in the curvature and in the commute times, it's also going to be important. So it's not only the one hop, but the k-hops. There should be a trade-off. We have to investigate the trade-off, because we have seen that in some graphs, even increasing the fairness will increase the accuracy if there is homophilia, heterophilia, insensitive attributes at this level. And then more important things that causality-aware GNNs, there are some methods from Chirag Agarwal and Marin Katsiknik that tries to incorporate counterfactual fairness, but we should go deeper in the causality, because I don't know if the current methods for GNNs are aligned with causality, not only in fairness, but also side fairness. And also there are the classical ethical challenges that we have also in algorithmic fairness. So there are different philosophical definitions, the human is in the lab, and the sensitive attributes are not always categoric, nor discrete, nor static. I put here because this is a takeaway from a blog that I don't remember right now, okay? So yes, that's all. Thank you very much. So here's the feedback form. So please fill this form to help Log1 fairness to improve, but also it's going to help us to improve more. And acknowledgements, thank you very much to all the sponsors, and also to Amek Vega, that it's co-author of the panel and has made a lot of content in the panel as well. And here's the bibliography, so you can watch it. And then now we have the panel discussions. Before ending the panel discussion, just a quick recap that the code and the slides are going to be public in the web page. So this is just not a once in a lifetime tutorial. We are going to keep improving the slides, keep improving the code and explanation. So I hope this can be an important toolbox in an important resource in your toolbox. Without more delay, we have a bit of delay, we are going to start the panel discussion.
Well, thank you very much. Maybe I'll quickly introduce the panel, and then I will pass it again to you, because unfortunately I have a family emergency and I'm not going to be able to stay for the entire panel. But we are super excited to have some of the world's leading scientists in graph, I guess, learning in general, and specifically in graph rewiring for this panel. We have Petar Velichkovic from DeepMind. We have Marinka Zygnick from Harvard University, Francesco Fabri from Spotify, and Francesco Di Giovanni from Twitter. And the panel will proceed as follows. Each of the panelists will have 5 minutes to give a short presentation to present a certain position around the topic of graph rewiring. And then we will move on to questions and discussion, both moderated by Adrian, and also questions that you might have for any of the panelists. So without further ado, and we can follow the order that appears on the slide, we can move on to Petar, and maybe he can make the 5-minute pitch from Petar on his views on graph modeling and graph rewiring. Thank you so much.
All right, thanks for the baton, Nuria, and thank you very much for a very fascinating tutorial. I enjoyed listening to it throughout. I don't think I will really need 5 minutes. I will just say on one side that I think graph rewiring, or generally this question of decoupling the computational graph from the input graph, is arguably one of the most important challenges of graph representation learning right now. And perhaps like it comes to the point where if you figure out the right choice of graph structure, it might even be more significant than the choice of graph machine learning model. And I kind of hammered down that point in the question that I already raised on the Slack, where I basically said, maybe we should think beyond just the word rewiring, because rewiring to me just implies that edges are being moved around. Sometimes, even if you want to just fix over squashing rather than anything else, you might benefit from introducing additional nodes. But then when you introduce additional nodes, you might also be introducing other kinds of benefits. For example, endowing your graph neural network with memory or different kinds of stack mechanisms, which, as we know from computer computation theory, allow you to go beyond the realm of, say, finite state machines and into the realm of push-down automata, Turing machines, and so on. So you get your very own differentiable computers if you do rewiring in this kind of way. So that would be my very short pitch.
Thank you so much, Petar. So I guess you are an advocate for rewiring. Lou, we're going to move on to Marinka. I hope she's connected.
Yes, I'm connected.
Yeah, okay.
Here. Excited to be here with everyone in this tutorial, as well as on the panel. I have a few, just 4 slides that I'd like to kind of go through to make the points that I'd like to make. So most of our research in graph ML is motivated actually by some particular problems in different application areas, and of those that we care a lot about are applications in medicine and in science, in particular therapeutic science. And so how is that relevant to the topic of today's tutorial, and in particular the various notions of defining the optimal graph structure for downstream ML use? And so what we are seeing is across these different areas, as we all know, it's very important and critical to be able to model the structure, geometry, and prior knowledge accurately. However, often we have data sets where graphs are not given naturally in the input, especially now the frontier of science. We are kind of moving away from this more classic and better studied applications where graphs are by design given to us. But we are entering the phase of having multiple alternative graph structure representations of the same data that can be used for the same downstream task. And kind of, I would strongly echo what Petar just said, then the choice of the graph structure then can influence performance on downstream ML more than the choice of a specific architecture. And so we've been thinking a lot about this question recently. In fact, we did a thorough survey of 145 studies of graph ML across different application areas, including those that traditionally are not thought of as graph-based domains. And so what we find in many of those areas, there are kind of two key challenges that I'd like to kind of bring to your attention. One is that increasingly we see graph data sets call for methods that can combine different kinds of inductive biases. And that kind of those biases can vary by the data modality or type of data that the graph model will be trained on. And it's often not explicitly given in the input. So the way I kind of broadly think about these problems now is that we are using GraphML in context of image-intensive graphs, where images plus graph structure is so prominent that images cannot be thought of as additional feature vectors, but really can be modeled, need to be modeled explicitly. Similarly, in the context of language-intensive graphs, where we have language plus graph strong relational structure data, either at the language level or at the additional data type, or where we have constraints given to us in the form of prior knowledge or invariances and equivariance. And across those 145 studies, what we have seen is that definition of graph structure, and that entails both defining what nodes are, defining what edges are, defining what connectivities, can vary considerably. It can depend on downstream use. So it becomes interesting to think about, is my goal to get robust predictions versus is my goal to have a model that can be the same model used across many different tasks. For example, if you want to reason about proteins, you might want to have a model where nodes are not only given at the protein level, but perhaps at the subprotein domain level. So you need to have this multi-scale representation. If you expect that the downstream task will require you to reason about proteins at different levels. And second, graph structure, definition of graphs, then also crucially kind of depend on what is the actual data modality that the graph model will be used on, because it's not anymore just necessarily a social network or a protein interaction network, but there are many other emerging modalities. So we are thinking a lot about this notion of decoupling the question of learning the structure that would be optimal for downstream task versus learning on the structure once that is given. And ultimately, like what we would like to move forward to is to have these two processes, which are now more or less completely independent of each other in prevailing literature, either being integrated more closely, or at least have many of the techniques that were presented in earlier tutorial used here. So I'll stop sharing here, looking forward to the discussion of this panel. And again, very timely topic for the choice of tutorial. I'm excited to be here today.
Thank you so much, Marika. Thank you very much. So I'm going to move on to the next pitch. Francesco, did you want to?
Yeah, I think I'm ready. I mean, I had thought of sharing a few slides, but now I changed my mind and I'm going to keep it short. So I think, I mean, it's not a surprise I'm here. That sort of like I'm very sort of excited and generally interested in the direction. Perhaps from a slightly different perspective, like to me, the most, what interests me the most is not when the graph structure is useless or we don't know how to construct such a graph structure, but there is a graph structure there that actually has a specific meaning. But the problem is with sort of the more efficient message passing networks we have at disposal, some topological properties of the graph may sort of compromise performance if you think about long-range interactions, but also like expressivity more in general. And the idea would be how we actually leverage the input topology and change it in an interpretable way to sort of mitigate these problems and improve expressivity, because these are techniques that have been used across like geometry for most of the last 50 years, and they've been extremely successful at classification. So the idea would be mostly like the graph structure has a meaning, think of molecule blueprint, but can I somehow learn transformations that improve the efficiency, the expressive power message passing networks, but in a sort of interpretable way? We know how the graph is evolving. So it's a more like perhaps theoretical question, but I think a very timely one, given that on the other side of the spectrum, there are methods that perhaps sort of like work more like a black box, but they in a way not account for the graph structure like GNNs do, think of transformers, and seem they might be very competitive. So I think it's a timely question, both from theory and, of course, practice.
Francesco Fabri?
Yeah, I want to just like probably like briefly, I give another like perspective on what we have seen today. So thanks for the invitation first, and like thanks for the tutorial. It was like exciting to see, especially connecting the two words, like the methodological and socio-technical aspect of the world of graph representation learning. And I feel that when we think about graph rewiring, we have to put an effort on as a community to understanding which is the definition, as Peter was saying also in the Slack. We definitely have to move there, understanding which are the implications of the way that we want to apply like modification on the graphs, especially when the context changes. And this is something that's also the other panelists like emphasize, that the way that we change context, fairness, and other, let's say, responsible AI area topics related to responsible AI brought to the table. For example, in the past, we saw that rewiring may have an impact on the accuracy, but also can have a positive impact on aspects like radicalization of the recommendations or fairness of the distribution of the classification tax. So I think that the way that we think about the problem can also be thought from another perspective, not only from the perspective of methodological issue, but also socio-technical aspects. So a fairness or algorithmic bias in general can help to shed the light of the limitation of our our nowadays architecture and to devise a better one. When we change the context, we change the downstream task, for example, the recommendation, and we talk about human beings, then thinking about the limitation of those models is not about methodological aspect, but like, yeah, there's a trade-off between the policy we want to include for reducing radicalization or fairness. So I definitely think that when we talk about those aspects, we cannot underestimate the algorithmic bias and the perspective of the right context to consider. And so we need also a shift in the language that we use, especially we talk about the metrics, right? So changing the context, we also change the way that we should evaluate those methods and thinking about how we can optimize the method, not only for better accuracy, but also better perspective of alternative ways of evaluating those.
Yeah, definitely agree. That's why we have included that part, the last part of fairness, first for thinking out of the theoretical box, and then for analyzing that both problems are correlated in somehow. The homophilia, heterophilia, you add one more homophilia, heterophilia, so it's very interesting. Yeah, so most of you have highlighted that maybe the definition of rewiring should be changed or should be augmented somehow, just to incorporate new, Peter has says, new nodes for theoretically nodes with memory. Marinka has highlighted like the difference between the rewiring and the, let's say, learnable structure. And also you have said that the meaning of rewiring should be different if you are in a protein-based scenario than if you are in a human-like. So what do you think that the community should like standardize this graph rewiring scenario? Which are the dimensions that we should look to properly define graph rewiring or augmented message passing or whatever definitions you. So for example, Petar, if you want to start, that you have been the one stating the opening the question in the Slack. So
right. So maybe I'll split my answer into two parts. First, I want to say something related to what Marinka said, which I highly agree with about the graph. Even when we have a ground truth graph, and often in nature we don't, even if we have a ground truth graph, it might be useless or very, very poor for the task that you want to solve. I'll just motivate this with a simple problem that I think will be good. Like if anyone attending this tutorial is not certain why they should use graph rewiring, this is a very simple one. Imagine you have a graph of n nodes, right? And all the nodes are initially disconnected. And you add edges to the graph incrementally, and you want your GNN to be able to answer questions of, are two nodes connected? Like, is there a path between them? Hopefully you can see that if I'm very adversarial about how I'm adding my edges, my ground truth completely correct graph, no noise in it whatsoever, requires linear time, right? Because the GNN needs to traverse this long path between two nodes to figure out that they're in the same component. But if instead I use my theoretical computer science knowledge and organize the edges in this graph in a slightly different way, specifically if I build a disjoint set union data structure where it doesn't track edges anymore, but it tracks connected components in a way that I can quickly query connected components. Now, suddenly with this choice of edges, my complexity drops from linear time to inverse Ackermann function time, which for all astronomically large values of n is less than 5. Right? So if I'm clever about my choice of edges, even for completely correct graphs, I can reduce the computational complexity that my GNN has to do to solve the problem. So there are many reasons why you might want to think about rewiring, even if you trust your graphs completely. That's the first point I wanted to make. And on the topic of defining graph rewiring, I actually recently saw a talk from Francesco Di Giovanni, which defines rewiring, in my opinion, in a very, very nice way that maybe we should assume going forward. So I would actually prompt Francesco to answer this question rather than myself, if that works.
Yeah, definitely. In fact, I wanted to ask, it's in the same scope that we have seen new approaches of rewiring, like a shift diffusion or gradient flows. So yeah, I would like also you to mention the difference between the classical rewiring and these new approaches, Francesco.
Yeah, so yeah, no, I think it's a good question, because I feel like the you know, and it's sort of part of what Peter was saying in his sort of position paper. The idea is like most of the community, you know, for a long time somehow has been using graph rewiring techniques where, okay, let's actually say, okay, what I mean, graph rewiring basically, I agree, maybe like partial, and the idea is mostly seems to allude to changing the sort of connectivity of the input graph. But more generally, you can think of, you know, you have a certain problem, and the problem may have a graph structure and some features in input, right? So, and you can think of, you know, a graph structure may be provided to you. You can build a graph structure on top of some entities, but somehow like there is such topological object in your domain. And then you may have node features, edge features, whatever you want, global features. And then in principle, like GNN, you can think of, you know, this parametric class of functions that take these inputs and give you a prediction, right? And of course, you can clearly see, for example, how trivially, for example, something like transformers can be seen as a subset of this general class. So I'm using the most possible general definition of parametric GNNs, right? But then the idea is, at the same time, is like we like to think of graph neural networks as like some iterative procedure, an architecture that goes through layers, and usually we think of message passing as sort of like the prototype of this framework. And the idea is like most of these architecture we have explored so far, like graph neural networks, they are in fact like message passing on a different computational graph. So the point of rewiring, more simply, is just that you can have an architecture that goes through layers or diffusion steps, if you like the continuous time approach, and it sort of propagates messages along edges of a given computational graph, but the computational graph is generally a function of the input graph and the features. So transformers, of course, may replace the input graph with a dense one, like a click, which is weighted using some attention mechanism. You can add master nodes that like now not just, you know, increase also the cardinality of the graph. You can have any transformation. But the key idea is like the way sort of you learn somehow is understood as like this propagation of messages, is how the computational graph evolves in your architecture that sort of matters, right? So, but then circling back to your question, I'm going to stop here. The point is, since the researchers have arguably been looking mostly at how do we define new GNN architectures, and usually this was like, you know, by targeting the expressive power question, like how can we define more expressive GNNs, then there is not really like a semantics or a, you know, a taxonomy for the different class of rewiring operations, and not even an understanding of the expressive power. So there's a lot to do there to sort of place all these things in order.
Yeah, that's great. That's great, and I think it's very relevant. Also, a couple of things that you have mentioned a couple of times is a difference between it has to be related with the theory, as Peter and Francesco Giovanni has said, that it has to be more interpretable in terms of whatever diffusion, curvature, or whatever. And in the other hand, you have these transformers or less, let's say, theoretically friendly approaches that are more. So I would like to ask to Marinka and Francesco Fabri, which are the ones that are applying rewiring more in the application setting, because even though, I mean, also from my point of view, has to be interpretable from the theory point of view, somehow if it works for protein folding, whatever, and Marinka's doing applications in healthcare and Francesco in society. So I would like to hear your thoughts in this, let's say, principle and versus non-principle rewiring, let's say curvature, diffusion, spectral versus transformers, greedy algorithms, etc.
Thank you, Adrian. I'd like to make 2 points. One, perhaps let me start with a kind of more broader view on. I like the term graph rewiring. I would bring to the attention that the word graph rewiring is actually the phrase kind of is also well known in graph theory to refer to how random network graphs are rewired to follow certain random to produce graphs with a specific degree distributions. Most famously, Mark Newman, one of the giants in network science, has developed his configuration model, which is a cornerstone of network science that is generated through a process that he refers to as graph rewiring. So why mentioning this here is primarily because I think the discussion we're having here on the panel and this tutorial also showed is that what we think of graph rewiring is much more broader problem or broader set of considerations than what, for example, graph rewiring traditionally represented in network science. So and it's not only about rewiring graphs edges that already exist, and it's much more. We talked about adding, dropping nodes, inferring the structure, and so on. So perhaps this calls for some kind of a bit broader, different revised name or a different taxonomy to organize this area of research. But kind of, I'm not saying that I have a solution to that problem. I'm just something that I wanted to point out when I talk to some of my colleagues from the network science perspective and mention this problem to them. They're often confused, and we need 5 minutes to just resolve what we mean by this problem. Okay, but now going to the second part of my comment, which is the direct answer to Adrian's question. So I think that both what you call as principled and unprincipled approaches have a role in the use of today's graph rewiring techniques and in different applications. It really depends on what is your application area, and I would more broadly say what is the downstream use of the ML model. If the ML model would be then particular, and the primary differentiator for that for me today is whether we would like to have a highly performing model that can answer a narrow set of tasks versus a more of generalist type approach that can be adaptable for a variety of different tasks. Let me give an example in the context of proteins. So proteins as on a canonical workhorse molecules are so interested that we might want to have a model that can, one model be used for a variety of different tasks. And those tasks, that the way they are defined, they are not all defined in the notion of a unit of analysis being a protein or a unit of analysis being amino acid. And so which are two extremes that are considered today in research. But you would want the same kind of model to have these representations learned and considered at multiple scales of that physical system. And a different relational structure exists at each of those scales of systems. We know how amino acids depend on each other, protein domains, which are subparts of proteins, entire proteins to each other, and so on. And so how that is something that today it can be resolved either in the input data representation by constructing these multi-scale hierarchical networks, or by using some form of hierarchical attention mechanism in the architectures. I don't think we have a good understanding of what would work better. And it would also depend on the computational efficiency down the line that you would like to to get. So I hope that kind of future research can resolve that to some level when especially in the context of natural sciences, where complex systems are organized as multiple scales. And then it's not even a question of having different graph structures that are convenient representations at each of those scales, but it would be known that certain structures are more or less optimal for different kinds of tasks. And so that's something that kind of we're thinking about a lot, where to integrate that knowledge in the overall ML workflow at the level of the input data, at the level of the architecture, at the level of the loss functions, at the sampling level. So we have had various levels of success in doing so, and don't yet have a definitive answer to that.
Yeah, definitely agree. I like your first part in which you have said that even starting to talk about rewiring as a concept, it's just a principal way of talking, and that now we are discovering that it's broader. So yeah, and Francesco, what are your thoughts about this? I mean, you're in your socio-technical context, Francesco Fabric. Even not only the methods, but also the metrics can be like even more specific for a suitable scenario. For example, I've explained the dyadic fairness metrics, but for example, these metrics that it's independence on the structure of the scientific on the sensitive attribute, maybe for a specific context in which you are doing recommendations in a blog, maybe a community of sensitive people has built a relationship, a safe space where they are like comfortable in the way, because they feel isolated in the real world, and then they have this safe space. Maybe this dyadic fairness doesn't work, and what they have to do is just they have to go out from nocive nodes in the network, as you did in your work. So I want to hear your thoughts both in the principal versus not principal methodologically, and also in the metrics. So
yeah, thank you. I wanted to start from a point that Marinka and I want to add on top what she just said, like confirming that depending on the application, depending on the point of the pipeline I want to actually analyze, the story can change a lot. And specifically, like when we saw now, like in the community, it's kind of the idea that when we test a downstream task, is important to bear in mind which is the level, for example, of homophily or heterophily in the graph, right? Because we know that this kind of component can change a lot of the story. But this is not enough, in my opinion, in the sense that to move step forward when we talk about specifically societal issues, so we don't have to stick necessarily to recommendation. We can also think about broad sense when we have classifications and we have to classify, and the data set is made by the nodes by our human beings. And homophily and heterophily can also be partitioned by groups. So it's not only the level of homophily of the whole graph, but it's by group. So like, and this can be symmetric, this can be asymmetric, and like story can completely change. So like, even if you keep it simple and you have like this graph and where the topology is even like expected to some extent, but for each single sensitive attribute that you consider, for each single protected attribute of the user, you will see different level of homophily and heterophily, then the story will change. And so what we should, like, I don't know, I don't have the answer now. I don't have one unique metric to, let's say, evaluate one problem at once, but I definitely, like, I see as a next step, like, if we really want to talk about downstream tasks, we should consider that if the model is supposed to be used for a socio-technical issue, then we should be sure that we have to be sure that the metrics is the proper one, and also the knowledge of the model is the proper one. Because at the end of the day, I think like the research that we do to improve the metrics or the accuracy of the models of the methodological aspect is orthogonal to which are the aspects of like explainability, fairness, or algorithmic bias in general. And so like the model that we do a choice of, okay, this is the best model that can fit our task for recommendation or link prediction, we should be sure that on the other side, this model is understood, like when it's deployed, it's like 100% sure it's not gonna create or amplify the bias. So recently we saw that studying this new phenomenon called algorithmic radicalization in recommendations, which the idea is that you give recommendation to the user, and there is a likely chance that depending on the way that the data are distributed, user may actually be stuck in a sort of rabbit hole. So the way that the user go back and forth in the feedback loop of interaction with the recommender, so while the user accept or reject a recommendation, the recommender is driving the user, right? And we saw that if you train a recommender at time 0, and you check you monitor the behavior, so you monitor the interaction between the user and the recommender, you will see that the data distribution, so by groups, so again, we don't look at the data as a whole, but we look at the different preferences. So there may be some users liking different clusterized by preferences. You will see that some bunch of users can actually drive preferences of the others. And so this is something that we don't really know at time 0 when we train a model, right? It's something that you should experience in the future. So having robustness in this sense, I think is tricky. It's not easy. Like, we have been investigating methods, but the job is not done. So like, we need to understand that like, when we have social technical issues on the side and we have like the application changes, we have to understand the impact of what we are doing, like the impact of the model. Even if this is best one in accuracy, we have to be sure that the implications that are in the field, in the pipeline, let's say.
Yeah, and I definitely agree that this is a thing that usually in human-centric machine learning, people usually takes into account from the first steps. But yeah, maybe the people that also works in more theoretical graph neural networks, notice Marinka that has explained that if you are doing something for a specific context, you have to explicitly analyze where it puts the value and analyze the things. But when we are doing like general GNNs, like attentions or like shift networks, do you think, all of you in general, do you think that when you are building a general GNN that is not applied to a specific context for proteins, whatever, like the recent advances or gradient flows or whatever, we should analyze this social component from the beginning, given that the graphs, like half of the benchmarks are, in half of the benchmark, the nodes are people, or what are your thoughts on that? I mean, not in the GNNs that are specific for the application, but in the ones that are general, like the ones that are currently proposing, for example, Francesco Di Giovanni. What are your thoughts? I know that there is a trade-off between applying this generally and having ethics from design or not. Yeah, that's the quote of the question. Ethics from the design, if it's general or no.
Yeah, it's a good question. So I think, so I have to say, the disclaimer is, I'm not a huge fan of like separating the community in works that are quote unquote regarded theoretical or general and works that are regarded as applied. Having said that though, I'm also aware that, like, for example, that, you know, the point is of working with general GNNs is like, the reason for why, for example, we care about the heterophily in the setting of node classification, right? So that most of the datasets we have at disposal, they're like stupid. Like, I mean, these datasets are not carrying any valuable information, and the task most of the times is made heterophilic because the label distribution is stupid. So why then we care about this? So on one side, right, the notion of heterophily that one would like to actually be good at is a notion of heterophily where the label distribution is somehow aligned with the graph structure, but in a more complicated way. If you think about the spectral domain, you don't want the label distribution to have most of its mass in the low frequency so that, you know, it's homophilic, but you would like to have some sort of correlation with the graph structure. Otherwise, if you pick a random label distribution or a random graph structure, you would be heterophilic, but then what's the point of using GNNs? This is why MLP in these cases are like extremely good. But there is a value, there is a value in doing that, which is effectively like stress testing architectures. So the problem is like, you know, why, you know, arguably, I think when you look at GNNs, most of the papers can be sort of, they contain now one of two things, like for papers that you call general GNNs, like expressive power. Am I more expressive than the 1WL test? Or am I actually avoiding oversmoothing? Now, it's quite limiting this perspective because, of course, we are most of the community now, I think, and I include myself in, we are sort of slightly stuck into now these frameworks that we know how to address. We know that these are sort of tools we can use to stress test the general GNNs, but there are also limitations, right? Because then we are limited by the benchmarks. So I think general investigation is always useful, but I think we are at the point where there's a lot to be done in terms of connecting more what we call like general GNNs, the theoretical problems, and to what extent these problems have an impact on the data sets we have at disposal. I'm not sure whether that answers your question, but that's sort of my point of view on the topic.
Yeah, it really answers. It really answers the questions. Thanks, Francesco. Yeah. I also wanted to remind that if you have some questions, yes, you can ask questions. I just read it in the chat, so you can ask questions. We only have like 5 minutes left because then there is a keynote from, I think, Soledad Villar, if I remember correctly. So yes, Shaitana, sorry for the pronunciation, has a question that is, can you talk about current GNN benchmarks? Do you mean dataset benchmarks, I guess? Yeah, okay. So the idea of the question, I guess, is like, from my point of view, is that whatever you're gonna show that your GNN is able to do, you have to test it with one mark or other, heterophilic, homophilic, neighbor matching, numeric algorithmic reasoning, for example, as well. So the relationship to graph rewiring and whether they can help advanced rewiring. I don't think I understand the last question. Okay, yeah. So there should be, if I can rephrase the question, there should be, he's interested in if there should be graph rewiring aligned with benchmarks, I guess, like benchmarks that are aligned with graph rewiring. I can remember now neighbor matching, but maybe some of you know more benchmarks where you can literally do it like rewiring. So yeah, it's an open question.
I can say something very quick about that, and then I leave, I don't know, maybe Peter has a better answer, but I think so in a way, sort of validating whether a graph rewiring approach helps or not is not terribly hard, I think, in the sense that, let's say you look at main instance of message passing on networks like, GCN, Gene, GraphSage, GAT, and then you can sort of validate whether by sort of change the computational graph on different type of tasks, node level and graph level and different data sets, whether the same architecture, statistically, there is a statistical consistent improvement. What is harder, I think, is in a way identifying exactly how the rewiring did help, like what was how the new computational graph actually helped. And for example, in the context of long-range interactions, again, we would love to say something about the improvement comes because we capture long-range interactions, but validating the actual reason for the improvement, this is usually much harder. So it's not much a problem of data sets, it's mostly a problem how we sort of, maybe we need to investigate a bit better, like the improvement of where this is coming from, because it may come from different things, like especially if we are thinking about rewiring or whatever you want to call it more general. So it's hard.
Anyone else has any thoughts on that? We have more questions if you don't have. Okay, we have one question on the Slack from Domenico Tortorella. He says, aren't we rushing to blame the shortcomings in properly training message spacing models on the input graphs? And he links, I'm gonna send it by Zoom, learning on graph paper extended Astra that they have done, in which they prove that they use untrained message passing and they outperform diffusion and curvature rewiring. So yes, the question is that aren't we rushing to blame the shortcomings in properly trained message passing models on the input graphs?
I think I can try to make some preliminary answer to that one. And I think that fundamentally there are two different questions at play here. So properly training message passing models to achieve a certain outcome, especially in the face of heterophily, like in this case, like I think those were the data sets that Domenico quoted in their paper primarily. And the fact that there exist proven effects of the graph topology on what any GNN, no matter how well you train it, are able to do. So basically, to answer the question of are we rushing to blame shortcomings of message passing with respect to the graph topology, I don't think we are rushing, because there exists a proof that under certain graph topologies, you can make the best GNN ever and train it in the best way ever, and you're not going to be able to allow these two nodes to communicate if that is relevant for your task, of course. So definitely studying the relationship of the graph topology to these kinds of effects is quite critical. But I think that is a separate issue and very important issue to also how to train a graph neural network model in a way that is robust to heterophilous edges or long range, trajectories or all those kinds of things. I mean, in algorithmic reasoning, we always have the ground truth graph, and we still very often struggle to find a solution that generalizes through simple gradient descent. So maybe the answer is we're not rushing, but we should be thinking of both of those problems at the same time, if that makes sense.
I agree. So, and the paper is very interesting as well. So we only have 4 minutes left, and the keynote starts at 7 o'clock. So maybe we can wrap up. If some of you have some final outline or highlight that you want to make, or some statement, or some just last thought that you can give to everyone, Marinka, Francescos, and Petar. So feel free to take the stage, unmute yourself, and give your last thoughts on this topic.
I think if I can start, I think the future is bright for the study of graph rewiring, and we kind of found through this panel that it's already a very broad topic, and I think it would be it will likely further expand in the future, where we are thinking of training these models on multi-model data sets, where you might have a relational inductive bias that would need to be combined with other biases, say that originate from image or language or prior knowledge data. And so then bringing that together with kind of the optimal graph rewiring for downstream tasks can be a fruitful area for research.
Maybe I can add also one point, which I think is quite interesting. I wasn't thinking of it this way. Like many people, you see a phenomenon being highlighted, like the over squashing, and you suddenly think this is really bad. We need to try to fight this. I recently was in a conversation with Michael Bronstein where he raised a very valid point that sometimes we want over squashing to happen. Remember that picture of two communities separated by one edge? If you have homophilic node classification, you actually don't want anything to cross that community boundary, actually. So what I would imagine would be kind of the ideal data-driven method of the future is something that not only rewires to ameliorate the global over squashing phenomenon, but one that like selectively squashes the messages depending on where they need to be squashed. And that's going to be a pretty interesting problem to try to attack in the future. Yeah.
Yeah, does San Francesco want to say something? I agree, Petar, with the dynamic rewiring and selecting the over squashing. That was one of the main points of DeepWire, trying to make like data-driven rewiring somehow. We're still working on that. So yes, so I think that's it. There's 1:30 seconds left. So thank you very much to everyone. Thank you very much, Marinka, Francesco Di Giovanni, Francesco Fabri, Petar Velikovic, for such an interesting panel. And thank you everyone that has attended the panel. I hope you had liked. Don't forget to submit your feedback to the feedback form in Learning on Graphs, and also feel free to send direct feedback to us. We will keep discussing about graph rewiring in the Slack channel. So thank you very much, and see you around the conference.